What is the electron configuration for phosphorus with 15 protons, symbol P? Now, the normal way we talk about electron configuration is by building them up using the strict aufbau schedule. Now, this is a schedule that has 2, then 6, then 10, then 14, and so on, building up subshell S being the 2, P being 6, D being 12, and F being 14. And you sort of go along a straight line and then up with these diagonal lines. So shell 1 is just the 2 and it's full. Schedule 1. Shell 2 is 2, then 6, then 2, then 6. And then strangely enough, you do 2, then 10, then 6, and so on. 2, then 14, then 10, then 6. So these aufbau rules are abstract. It's just numbers. Okay. Further, the most important rule here is that partial subshell filling is allowed. Let me show that. So when you do 1, 2, then that's full. 1, 2, and that's full. And then you just count 1, 2, 3, 4, 5. So you can have partial subshells. Now, further, you have that filling order that I discussed, the S, the 2, then the F, then the D, and then the P. And finally, there's this rule that really causes those diagonals where subshell D fills with the N, but the energy is N minus 1, and subshell F is fills with N, but the energy is N minus 2. That's sort of how these go up. So subshell 6 has the same energy as subshell 4, but its filling doesn't happen until it gets to 6. So those are the rules of the strict aufbau system, which is what's been taught in the textbooks for centuries. But what I'm going to talk about is creating subshells as a geometric system, as longitudinal rings of electrons. So I believe that things at the same inclination angle or longitude angle. Remember, an inclination is the angle from the pole to the position, and a longitude angle is from the equator. And since I'm using the pole, I prefer the wording inclination. But if you're thinking of this like a globe, which you also can, the word longitudinal is interchangeable. Those two concepts are complementary. If it's at the same angle and the same distance from the nucleus, thereby it'll have the same energy to fall into the nucleus, and the same energy to pull it to infinity, called as ionization or release energy. Further, there are two hemispheres. This hemisphere is one ring, and this hemisphere is another ring. Now, I believe that this is my interpretation of the Nobel Prize winner Bose in his 1924 paper that was a proof of statistical mechanics. And in that, I find a couple pieces of wording. First, he talked about a cylinder surface. Well, there it is. That looks like the surface of a cylinder. The electrons are out here, but all want to go into this central axis, the nucleostatic axis. And then to make his equations work later on, he said, well, I need to multiply everything times 2. And I think that's polarity. Well, to me, that's two hemispheres. Everything gets doubled up. Further, there's another thing about that structure, and that is this one is front and the one in the other ring is back. So the meridian, the start of any of these rings, is opposite. But as you draw straight through, that means this is 180 degrees versus the polyhemisphere pair in the same subshell, but at the 180-degree position relative to the nucleus. So everything comes in these two hemisphere pairs, but this is offset by 1/2 phase, which causes many things. Now, most of the time you'll see this is a description of the subshell 2p, and the underlying picture is this statistical mechanics electron distribution. What I'm saying is that this cylinder shell is the center of those two longitudinal sets. In fact, when you have these sets of multiple incomes all pointing towards there, they bounce into each other. So you get quantization, multiple items that bounce off in units of one electron. And that means only when you have a nucleostatic axis and you have multiple shells, multiple electrons in subshells off the center line, off the nucleostatic line in two hemispheres, do you get the Bose cylinder in two. And that's the only way to get statistical mechanics. Statistical mechanics does not work for just one electron all there standing by itself. There is no quantization of bouncing off of units of one or bouncing off somewhere the two of them, that quantization method that's famous. In fact, that pulling towards a central axis is Euler's formula that this particle would seem to be going to some axis and would get e to the ix as the formula. And you can see this in Schrodinger's equation when you get to advanced statistical mechanics. However, my work is to show that that particle 2 is the nucleus, and thereby I can eliminate that I, that imaginary number, although I hate that word and usually call it the invisible number. And if you know where the nucleus is, and because you have all these matching rings from this and other subshells, you know where that nucleostatic ring is, I eventually show an equation that eliminates that e to the ix and comes up with the same answers. It doesn't break anything that Bose says, it just becomes with a better frame of reference. Now, that better frame of reference also works very seriously to change that aufbau filling rules. You can see this is one hemisphere, and there is another hemisphere up off the top of the page. And so instead of it being 2, 6, 10, 14, it's 1, 3, 5, and 7 in each subshell. Now, the reason for that is because of this two hemispheres by the tightest packing. You see, 1 is 1 squared. 1 plus 3 is 4, but that's also 2 squared. 1 plus 3 plus 5 is 9, but that's also 3 squared. And 1 plus 3 plus 5 plus 7 is 16, which is 4 squared, and so on. So every time you look at this, you have basically a circle, and you're trying to get a number of units into that circle, which is pi times radius squared. But the radius is a unit of one electron. So you get the numbers squared, 1, 4, 9, 16. But that's the tightest packing in two hemispheres. In the other hemisphere, in the other direction, that's two dimensions. In that third dimension, you have this hemisphere structure that I showed you. Now, the other thing about this structure is that it has a preference towards the pole. The weak nuclear force is applicable because one of the particles, the nucleon, has a physics color. I don't know where they got the name, but that means that they line up along the poles. Now, off the poles, remember, this is not 3 here, but that's a ring of 3 and a ring of 5. But that means because of these, if you have 2 and they line up, you can offset them by half phase and they can get a little tighter. And again, everything wants to be pulled up to the Bohr radius in tightness to the nucleus. So as a result, you get 1, shell 2 becomes 3, shell 3 becomes 3, 5, 5, 7, 7. And that the periodic table that we all look at is based upon this physical logic of 2 hemispheres times pi r squared, so units of 1, 4, 9, 16, but interlaced so you get 2 layers after the first, which is just tiny, filled. The other thing, though, that means is that the distance here, those are all lined up on the axis, but that path is slightly longer. It gets sort of scrunched up so that this distance 7 for the 7 ring is effectively on a curve like shell 5, n minus 2. And this one here, sorry, looks like it's with shell 6. So as a result, you get a structure where the shells fill from pole to equator generally, but also with the energy levels of these higher towards the equator electrons being slightly higher. And so then really it's not a hemisphere, but really a hemis oblong. But nobody likes that word. So to do this, I've now put this into the Arno-Dot-Diagrams. Now this is similar to a Lewis diagram, but I don't like Lewis diagrams. It doesn't help a student to understand what's really going on in 3D engineering. You see, it has 2 electrons on this side, 2 electrons on that side, 2 and 2, always doing an octet. But that's not how the structures work. First, that second electron is all the way over on the far side, okay? Second is you have not just 8, but you have these other rings. So I set up the 3D engineering rules for an Arno-Dot diagram that's based upon 2 hemispheres, there they are, and only full subshells allowed. That is, I don't let us have a partial filled subshells because you would not get that statistical mechanics behavior, and the shell would effectively collapse or be imbalanced, and only this. But with 1s and 3s and 5s, you can get basically all the numbers. Well, not quite. You see, there's a transitional equatorial subshell of 3, and maybe 4 or 5 if you get out to xenon or something very, very big. Now, in those cases, you basically have an electron subshell, but the height of that cylinder is 0, so you don't get the doubling. So that means normally you always have these 2 pairs, so it's always even numbers. But many elements in the periodic table have odd numbers. So that comes with the addition of this equatorial set of 3, which is only transitional and not found in regular, in a full subshell. Now remember, these things have only full subshells, and a preference order is the tightest fit, working from the poles to the equators. But remember that that's not fair. If I have 8, say I have 1, 2, 3, 4, plus 4 is 8, that's fine. But if I have 10 in the outer subshell, I can't build there because this would be a incomplete. We can't have a partial subshell. But I can have these 5 full, that empty, and that empty, plus another 5, and that would be only full subshells, okay, and structures that are built in the of only full subshells, and it would be this full shell jumping to that far end, which we've already seen. Now, for the particulars of this video, I'm going to now, with that background, be able to talk about phosphorus. And phosphorus has a count of 15 and the symbol P. And we're going to talk specifically about first contributing phosphorus, okay, which has a +5 valence. Now, in this case, though, you already have an inner shell 4, which is the corners of the cube, 2 on the axis, 1, 2, and 1, 2, 3, 4, 5, 6. That one's hidden at the corners of the cube. However, those are all filled. So the phosphoruses, if possible, have a different configuration. It's the faces of the cube, or what I would say is a pyramid. So between these four corners, there, 1, 2, 3, 4, this electron sits up above the face right in the center. So 2, 1, 2, 3, and then on the back other side, 4, 5, 6. Now, the thing is, you also still have the option of having an equatorial, okay? And you have the two poles, of course, because those are always building up, okay? But it becomes faces or equatorial. Because the maximum of the shell is 8, you can't have 6 plus 3, that would be 9, okay? Now, phosphorus, though, is a different sort of structure that has to have the plus 5, okay? So can't use a 6, that wouldn't be full. But you can use a 3 plus 1, getting you the 5 valence. Thank you.